All right, this is lecture 3 of 3 for chapter 7. So we did a lot of the groundwork in the second lecture, so this lecture should kind of help tie all those pieces together and will definitely be shorter, fingers crossed. Okay, so lecture 2 really focused on this figure, and we talked about this figure in the context of our quantum numbers. So quantum numbers are really just a way of pinpointing a electron within a atom, right? And we're going to expand on that and look at electron configurations to specifically talk about the composition of electrons and their location in a particular element, which is pretty cool. So remember this section, which is really just looking at the rows of our periodic table, is going to be our N, which we can just think of as our energy level. So as you go down the periodic table, increasing the number of your rows, so 1 to 7, you're having higher energy shells of that atom, increasing complexity to the atom. Here we have those orbitals that comprise our shells. So we have s orbitals, we have d orbitals, s, d, p orbitals, and here we have our f orbitals. Those are the lanthanides and the actinides. We don't really talk about those very much. Okay, so it's essentially what we used this figure for, and now we're going to see how we can write electron configurations from that. But before we get there, we need to just dive a little bit deeper into these the differences in energy levels within that N level. So if N equals 1, we only have one orbital, and we know that that's an s orbital. If we are at N equals 2, we have s orbitals and p orbitals. And notice, so N equals 1, we have our lowest energy level, most stable. It's just 1 or 2 electrons really close to the nucleus, relative. N equals 2, we have our s and our p orbital, and notice that the p orbital is at a slightly higher energy level than that s orbital. And then we have our S, our P, and our D once we get into N equals 3. Okay, so we've talked a lot about this throughout the course of this class, but basically nature is going to reduce down to its most simple state. It's called entropy, and the more complex something is, the more energy it takes to hold it together, right? Think about how much food we have to consume in order to keep our bodies together in our fight against time. So what's important here is that these lower energy orbitals are going to fill first. So most stable going to more unstable. And if we look at our periodic table, this is just the first couple rows, omitting the transition metals, which would be down here after you get into N equals 3. We have this really nice kind of simplified version of our periodic table that we can use to start talking about electron configurations. So a principle with electron configurations, and what I was just talking about with those energy levels and always filling the lowest energy level first, right? We're not going to expend more energy than we have to, is tied in with this off-bow principle. So we know that the difference between hydrogen and helium is 1 proton, right? So we have protons being the defining characteristic of an atom. Hydrogen has 1 proton, helium has 2 protons, right? It is helium because it has 2 protons. If we are talking about an element that is neutral, you have to have 1 electron for every proton. So what the off-bow principle is saying is just like we have protons filing into the nucleus to make increasingly complex and larger atoms, we have the same thing happening with electrons. They're filing in one by one, kind of, you can think about it as happening like in tandem with those protons. So here we have our s orbital, and you can think about helium as just being kind of nestled right here when we are looking at the periodic table for electron configurations. So helium. So this would be n equals 1. We know in n equals 1 we only have one shell, and that's going to be, or one orbital within that shell, and that's going to be an s orbital. And that s orbital can hold 2 electrons. So in order to have 2 electrons in our s orbital, we would have to first fill a proton and electron that would represent hydrogen, and then we would have to fill a proton and an electron to get us to helium. So you have this filing in. So for lithium, you can't have lithium until your 1s shell is full. So we think of this as, if n equals 1, we would write that as 1s, right? So 1 being our n level, energy level, s being the shape of our orbital. And we have to have both, we have to have that orbital completely full, which can hold 2 electrons, so that would be 1s2. This would be the number of electrons in the orbital. So if we were describing an element and we said that its electron configuration was 1s2, that element would be helium. If we had n equals 2, we can only achieve n equals 2 if our first shell is full. So that would mean that we would have 1s2. And then let's write the electron configuration for lithium. Then it would be 2, right? That's the next n level. S1 would be lithium. 1 electron in that s orbital. If I was talking about beryllium, it would be 1s2, 2s2. At this point, my s orbital is full. I have these p orbitals that are part of that n level, but there's no electrons in them, right? Let's say I'm sticking to n equals 2, and I want to talk about the electron configuration of oxygen. I would have 1s2, right? That first shell has to be full before I can even have a second shell. This would be 2s2. That gets me, again, to beryllium. Then I would have 2p, right? Now I've jumped over the valley of the periodic table. I'm in the p zone. Yep, p zone of the periodic table. And I am only going to oxygen. So again, this is where the off-balance principle comes in. So these protons are filing in, and so are electrons. So I'm in my 2p orbital, and I have 1, 2, 3, 4 electrons. So it would be 2p4. This is the electron configuration of oxygen, which is pretty cool. So electron configurations are really just building off of what we talked about and this understanding of lower energy shells having to be filled before you can add to the complexity. That makes sense. That's the way our elements are formed. So here's that same lovely figure that we've been just beaten to death. And this is a nice chart that I put together for you guys, just summarizing that last little bit of information in the last lecture, so lecture 2 of this chapter. So we have these 4 different orbital types that we're interested in. The number of like lobes or subshells within, or suborbitals in that larger group would be 1 for S, right? That's just a sphere. P has 3, it's those lobes. D gets a little crazier, F gets even crazier. And each one of those lobes or subshells, suborbitals, excuse me, can house 2 electrons representing that positive 1 half spin and negative 1 half spin. So it means that an s orbital can hold 2, a p orbital can hold 6, a d orbital can hold 10, and an f can hold 14. So notice that's 1, 2, 1, 2, 3, 4, 5, 6. D is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. F 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so those electrons filing in, right? Increasing our complexity. Here's another chart that I wanted to give you guys, or figure for looking at the periodic table and how it's blocked off. This one's a little bit more clear cut. I think I like this one a little bit better because it shows you how to factor in these F orbitals. So you would fill your F orbitals before D. We're going to get to that. Don't stress it. But it's also nice and color coded and just a little bit more simplified. So just something to think about. Use either figure. Obviously, your exam and quiz are online, so you can do whatever you want. Okay, so let's do a whole bunch of examples. And I kind of want to get this one too. Hold on. Okay, so I really like this figure because it is showing you the way that these orbitals are going to be filled. So you're just tracing the line like I'm doing with my mouse right now. I find it to be a really helpful visual explanation of what we're doing here, because we're going to see things get kind of tricky once you start going into d orbitals and f orbitals. So let's just go ahead and do a couple more simple ones. I don't have a periodic table with me. There's a periodic table is never far from me. Yeah, brag about it, right? Okay, so let's do a couple examples. I just woke my dog up. He's really mad at me. It's okay. Okay, so let's start with aluminum. Yeah. So when you're writing the electron configuration of aluminum, the first thing that you want to do is just look and find it on the periodic table. And I can see that it is in row 3 of the periodic table. So it is going to, in order to be in row 3, all of those other electrons and protons have to be filed in, right? So we have to talk about, or we have to show the electrons filing into these lower energy shells first. So in order to be in n equals 3, my n equals 1 has to be full. So n equals 1, that's an s orbital, it can hold 2. So now I've filled, that represents both hydrogen and helium. Now I go to my second row of my periodic table, and the first thing to be filled would be my 2s2, which would represent lithium and beryllium. Jump over the valley of the periodic table and you get to 2p. I know that that's completely full, and a p orbital can hold 6, right? Representing boron through neon. Now I can go down to my 3s. My 3s is full, representing my sodium and magnesium. So then I get to 3p. Aluminum is the first one in that column, right here. So this is the electron configuration of aluminum. Very cool. So in order to have one electron in that p orbital, all of these orbitals have to be full, right? Lowest energy orbitals get filled first. Okay, let's do another example where we're going to have to incorporate a d orbital. Okay, so let's go ahead and do iron. All right, I said it incorporated a d orbital. We know that that doesn't happen until we're at an n of 4. So we know that we have to fill up all of those shells leading up to an n of 4. So that'd be 1s2. Right, now I'm in helium, 2s2, beryllium, 2p6, neon, 3s2, getting me to magnesium, 3p6, getting to argon, 4s2. And now this is the cool part. So if you look up at this figure here, We have 4s, and then my d is actually of my has a lower n number. So a really interesting thing is happening here. So these d orbitals have electrons that are like further away from the nucleus. They're really high energy. And so what we end up seeing is actually the 4s orbital is at a lower energy than the 3d orbital. And so it actually gets filled first, and it kind of shields those d orbitals. So 4s2 is going to be filled first, and then my 3d orbital is going to be filled. And I'll have 3d, 1, 2, 3, 4, 5, 6. Right? Because iron is 1, 2, 3, 4, 5, 6. Right there. So one way that I try to remember that is, this is the valley of the periodic table. I like to think of it as stepping down into that valley, so that N level is going down one as soon as you're working with those transition metals. Now, interestingly, and let's just go ahead and do one of these. Let's do tungsten, right? Because I just read a book by Oliver Sacks that was all about tungsten, and I really liked it. Again, I am so cool. Okay, so tungsten is in row 1, 2, 3, 4, 5, 6 of our periodic table. So I got to fill up everything leading up to it. So that is 1s2, 2s2, 2p6. Notice I'm just following this: 1s2, 2s2, 2p6. Oh, 3s2. Oh God, craziness. Let me let that go away. Okay, W. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, right? 4s2, 3d. Remember, D can hold up to 10. If you don't remember that, you can just count across. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Cool. So 3d10 is full, and now I'm back in the p orbitals, which are one step up in my energy level, 4p6. Now I'm done there. I'm ready to head into 5s2. And I go to my 4d10, 5p6. Then, so 5p6 is filled. Now I'm at my 6s2. Okay, and now before I fill my 5d, and that's what this is trying to show, before I go to 5d, I have to fill my 4f. So this is going to be my 4f14. Then I go to 5d, which is where tungsten is, right? 1, 2, 3, 5d, 1, 2, 3, 4. Whew. So that would be the complete electron configuration of tungsten. All right, you're going to want to get a ton of practice with these. One really cool trick is that if you look at this electron configuration of tungsten, notice this 1s2 would be the electron configuration of helium, a noble gas. 2s2 to 2p6 would be the electron configuration of neon, right? So that would also encompass the 1s. If I had everything that preceded it and my 3s2 and my 3p6, that would be argon. If I continued and I got all the way to my 4p6, that would be krypton. 4s2 all the way to my 5p6, and I am at xenon. And then I don't have a complete 6, n equals 6 shell here. But what I can do is a shortcut for my electron configuration. So this, what I did here in this first exercise, is our complete electron configuration. Now, I'm going to show you the shortcut version. So the shortcut would be, okay, we want to talk about tungsten. All right, well, what's the preceding noble gas? So you look at tungsten is in row 1, 2, 3, 4, 5, 6. So I want to look at the noble gas in row 5, and that is xenon. So what I'm doing here is I put this in brackets and I'm saying, hey, you know the electron configuration of xenon? Write that, or imagine that that is full, because I can't have tungsten unless I had all of those preceding shells full. So I can just be like, check that out. You're smart, we're smart, let's move on. And this becomes the abbreviated or shortened electron configuration, which is really nice. Do not start with the shortcut. You need to do a lot of practice writing it out completely in order to get comfortable with this. But once you are, you can really, really help yourself. This is a good tool, especially when you first get started. But what you're going to end up finding is that you're just reading the periodic table. Just need to remember that if you're in the transition metals, you drop down in one N level, and the lanthanides and actinides are going to drop down one as well. Okay. So those are electron configurations. They're specific. Each element is going to have a different electron configuration. Now, let's just do one more example, and we'll make it simple because it's not a crazy concept. But let's say we were looking at the sodium ion. So the sodium ion, notice it has a positive symbol, right? We know that that's a cation. It forms a positive 1 cation. That means that it has one less electron. Okay, so let's just go ahead and write the complete electron configuration. 1s2, 2s2, 2p6. Now, sodium is in group 3, or row 3, excuse me, and it would normally be 3s1, right? If it was not an ion, but it is an ion. So it is 1s2, 2s2, 2p6. Notice that is also the electron configuration of neon. So this whole chapter, not even this whole chapter, this whole semester, we've been talking about these trends in ions and some bonding trends. And what it really gets down to is that sodium wants to lose one electron, because if it does, it achieves noble gas configuration, and it's really, really stable. So we've talked about the fact that it's really, really stable before, but now we have some kind of justification or understanding of that. Okay, so there's one other way of representing these electron configurations, and it's using orbital diagrams. So this is just like one more layer of understanding. And so the big considerations here is that we have Hund's rule, and then we have the Pauli exclusion principle. So here we have the lowest energy configuration of an atom is the one having the maximum number of unpaired electrons. It's Hund's. And that's allowed by the Pauli principle of a particular set of degenerate orbitals. Okay, so what does that mean? Before we were representing our orbitals just by using a superscript. Now our 1s orbital would be a single box showing that it just has one orbit. It doesn't have multiple lobes. 2s would be a single box, and then our 2p would be 3 boxes representing the 6 electrons that can fill it. So each box can hold 2 electrons because those boxes are representing orbitals, right? S only has 1 orbital. P has 3 orbitals. So our 1s orbital has to be filled before our 2s orbital. So this would be our electron configuration, and this would be our orbital diagram. Now, orbital diagrams are really nice and kind of are giving us a deeper understanding because they really clearly show that these 2p orbitals are degenerate, which means they're at the same energy level. So if they're at the same energy level, what we find from the combination of Hund's and Pauli's rule is that electrons are not going to occupy the same orbital together if there's an empty degenerate orbital that it can file into. So what I like to think about this is like, okay, 1s, I can't have a 2s unless I have 2 electrons that are spinning in opposite directions in the same orbital. Same thing for my 2s. As soon as I get into my 2p, I have like a little bit more room to roam. So I like to think of electrons as being like adults. So for the typical adult, you do not have a roommate unless you have to have one, right? So I have a roommate because I have to have one. And that's great, right? Love roommates. But if I made enough money, I would not have a roommate. I would live alone. It would be me and my dog, and it would be awesome, right? So electrons are like adults. If they can occupy their own shell, they will. So if you see here for carbon, we have the electron configuration of 1s2, 2s2, 2p2. You could think that, okay, yes, we have our 1s. We usually just draw these as single barbs. That just didn't exist in PowerPoint. You would easily think, oh, sorry, let me get rid of that. Easily think that with carbon having 2 electrons in the 2p orbital, that it would look like this. But that would be incorrect, right? Because electrons are adults. They want room to roam. It's actually just more stable. So they're both going to have a positive 1 spin, which we represent by this up arrow with just a single barb. Down arrow would be a negative 1/2. So before doubling up, before having roommates, they're going to live alone. So this is carbon. Nitrogen would have, here actually I have an empty slide coming up. Let's look at the orbital diagram of nitrogen. You have to label your boxes. Otherwise, they're just boxes. They don't mean anything. All right, so nitrogen is in row 2. It has these p orbitals. So 1s gets filled, 2s gets 2. And nitrogen is 2p3, right? Nitrogen 1s2, 2s2, 2p3. So those are going to file into degenerate orbitals. If we were talking about oxygen, we have 1 more electron in the p orbital, right? It's 1s2, 2s2, 2p4. So that 4th electron is going to file in to, we can think of this as our px, right? That would be px, py, pz. It's going to file in next to it. Okay, so let's go back to oxygen. Fill each box individually before you pair up. Okay, so this would be my neutral oxygen atom. Now, I'm going to introduce you to a new term in this class, but most of you, if you took in chemistry in like high school, you have heard of this. And if you watch the video, these n equals 2 shells, that highest energy level, these are called our valence electrons. Valence electrons are going to be the electrons involved in bonding. This, or if it's a larger atom and you have more if you're at like n equals 3, anything that precedes that n level are called your core electrons. And they are not involved in bonding. Okay, so let's think about the kind of ion that oxygen typically forms. Or the charge that oxygen likes to have. And that would be O2 negative, right? It's in group 6A. So if you think about that, this is going to be gaining 2 electrons. Those electrons would file in. I'm just going to make these fat to represent that these joined us from another zone. The electrons would be filing in right there. As soon as that happens, then we have noble gas configuration. Oxygen looks the same as neon. We know that noble gases are super stable. So we're going to talk a lot about this in chapter 8. But for now, let's just leave that there. We just have one last slide. So we just covered valence electrons. It's the outermost principal quantum number. So what that's saying is your n level, right? Principal quantum number. They're essential for bonding. Core electrons are those inner electrons. And this is a really big concept. So in the periodic table, elements in the same group, right? Group is column. They're going to have the same number of valence electrons. That makes sense, right? So we look at sodium, and we know that it likes to form a +1 cation. We look at potassium, likes to form a +1. Lithium likes to form a +1. They all like to lose 1 electron to give them noble gas configuration. So we've already talked about this relationship, that if you're in the same column, you have the same chemical behavior. Now we understand that that chemical behavior and what I mean by that is like ion trends and bonding is due to electron configuration. Yeah. Okay, so we've already kind of talked about that a little bit in this class, but this is the first time that we're really putting it on paper, if you will. So that is it for chapter 7.